Since the turn of the century, the United States has undergone a phenomenal growth in population and industry. The availability of economical electrical power has been a major influence on this growth. Our requirements have more than doubled every decade for the past 40 years, and even greater demand is predicted in the future. The growth and development of practically every nation in the world is likewise being influenced by the availability of economical electrical energy. Simultaneously, fossil fuels are becoming an important source of raw materials for the manufacture of new and valuable products. The projected lifetime of normal fuel sources is, therefore, rapidly diminishing, despite exploration and improved techniques of recovery, and the cost of generating electrical energy is expected to increase. The United States Atomic Energy Commission is developing nuclear energy as a source of economical power to meet increasing power demand throughout the world. The power demonstration program is aimed at demonstrating the potential of various types of nuclear power reactor systems for central station power applications. Data from the design, construction, and operation of these plants are used for the design of subsequent plants, in keeping with the Commission's goals for developing economic nuclear power. The Commission's reactor development program also provides for the development of advanced concepts requiring a higher degree of technical refinement. One of the various concepts being developed, the natural uranium-fueled, heavy water moderated reactor, has potential for achieving economical power because of the relatively low cost and greater availability of natural uranium as a fuel, and the characteristics of deuterium as a moderator. Such a plant would be independent of costly facilities for the enrichment of uranium. The availability and cost of heavy water to moderate such a reactor had always been a problem in development of this concept. In 1952, a new AEC installation, the Savannah River plant, became operational. Located near Aiken, South Carolina, the plant would be operated by the E.I. Dupont de Nemours Company under a prime contract administered by the Savannah River Operations Office of the AEC. The AEC's Savannah River plant, built to produce plutonium and other vital nuclear materials, includes a heavy water extraction facility. Production of deuterium in the form of heavy water, or D2O, from this plant, at one time more than 1,000 tons a year, provided the moderator for Savannah River production reactors and other requirements of the AEC, including both foreign and domestic sales. Heavy water costs have been reduced from $70 a pound to $28 a pound. A research and development facility, the Savannah River Laboratory was established to perform diversified investigations, with emphasis on the technology of heavy water reactors. In November 1956, Dupont was requested to extend its activities to include the investigation of natural uranium heavy water power reactors. A study of reactor design concepts in the 100 electrical megawatt range was initiated. This was the minimum size that was believed to be economically attractive for development in the United States. Early investigations, however, indicated that none of the concepts studied in the 100 electrical megawatt range could compete with fossil fuels, even in high power cost areas of the country. A continuation of the study with design investigations of 200, 300, and 400 electrical megawatts was performed. Results indicated that a sizable reduction in power cost was possible in larger sized plants. Additional development of reactor components and fuels was required to reduce capital and operating costs to competitive levels. To carry out this program, it was determined that a facility would be necessary for full-scale testing of fuels and reactor components. A conceptual design of a test reactor was developed. In November 1958, authority was granted to proceed with the design and construction of a test reactor to be known as the Heavy Water Components Test Reactor, or HWCTR, and located at the Savannah River plant. The site chosen for the HWCTR was easily accessible and could use existing supporting facilities. Design was initiated, ground was broken, and plans advanced for construction of the HWCTR. In addition to the test reactor project, the AEC's Savannah River Operations Office was assigned responsibility for development of natural uranium heavy water power reactors concept. As a result of studies, it was determined that a pressure vessel liquid-cooled reactor could probably be built with existing technology. However, a more advanced design, a pressure tube boiling direct cycle reactor, indicated lower power costs and the greatest promise of being economically competitive with conventional power plants. 5 major areas required additional research and development to confirm feasibility prior to constructing a prototype heavy water power reactor. Lattice studies to determine optimum fuel lifetime and studies of safety and stability. Fuel element selection and development of inexpensive fabrication techniques. Studies of heavy water heat transfer, chemistry, hydraulics, and leakage problems, especially vapor losses at high temperatures and pressures. Selection and evaluation of special components for heavy water reactor service. The possible use of conventional materials and components for lowering capital costs. A program to study the physics of heavy water lattices was initiated to determine optimum design parameters. The Process Development Pile, a large critical facility of the Savannah River Laboratory, was modified to permit these studies. The large stainless steel tank, holding over 100 tons of heavy water, permitted studies in a broad range of lattice arrangements. both uranium metal and uranium oxide fuel materials were investigated. Special facilities permitted subcritical screening studies and extension of data to conditions of elevated temperatures and pressures. Data from these experiments was analyzed on high-speed computers. The performance and safety characteristics of various conceptual designs were also analyzed and predicted. The fuel development program included a systematic search for low-cost methods of fabrication. A process of co-extruding tubular fuel elements of uranium metal with a zirconium or zircaloy cladding was developed at Nuclear Metals Incorporated. Proper design of the extrusion billet permitted variation of core and cladding dimensions. Fuel tubes with core thicknesses of 130 to 250 mils and lengths of 10 feet were produced for irradiation tests. Driver fuel and the metallic uranium test fuel for HWCTR was produced by this process. Alloys of uranium, such as uranium zirconium and uranium molybdenum, were studied to improve dimensional stability under irradiation and increase corrosion resistance. Samples of these fuel elements were irradiated in the Savannah River production reactors, the Valicitos boiling water reactor, and the E20 loop of the NRU at Chalk River, Canada. Post-irradiation examination of fuels in high-level caves was performed at Savannah River to guide development of the fabrication process. Because of the inherent corrosion resistance and improved stability of uranium oxide, techniques for the inexpensive manufacture of UO2 fuels were also investigated. Methods of assembling individual compacted pellets were well established, but were relatively costly. Long rods of UO2, compacted by mechanical vibration and swaging of the zircaloy sheathing, had been produced in connection with other programs such as fuel elements for the plutonium recycle test reactor. Work was begun at Savannah River Laboratory to produce a tubular fuel element of vibratory and swage compacted UO2. This process, combined with tubular configuration, showed promise of reducing the number of fuel pieces and operations required for an element, thus reducing cost by simplifying processing and assembly. Under this fuel development program, candidate fuel elements of both uranium metal and uranium oxide were manufactured for testing in the HWCTR. In addition to the metallurgical and physics studies, investigations were conducted concurrently at the Savannah River Laboratory's hydraulic test facility to determine the leakage from various components of the heavy water circulating system. Specifications for components of the HWCTR were developed in this program. Data were also obtained on the corrosion and vibration of fuel assemblies exposed to simulated power reactor coolant conditions. The experimental heat transfer loop systems at Savannah River Laboratory and at Columbia University provided needed engineering data. In Included were studies of fuel burnout and hydraulic stability of a boiling water reactor. Further development in all these areas would be extended by construction and operation of the HWCTR. Subgrade structure for the HWCTR required removal of approximately 50,000 cubic yards of earth. The excavation measured approximately 200 by 200 feet at the surface and was 60 feet deep. A monolithic slab of concrete was placed as the foundation. The internal concrete structure, consisting of the reactor biological shield and spent fuel basin, was erected next. The reactor building used a new concept for vapor containment design and construction. Reinforced concrete was used below grade, attached to a carbon steel shell above grade. Its overall dimensions are 70 feet in diameter and 120 feet in height. Tensioned steel strands are used to strengthen the concrete shell against internal pressure. The 18-inch thick concrete shell was placed in one continuous pour. After sealing the outside of the concrete wall and backfilling, the 65-foot-high dome portion was bolted to the concrete at grade level. The building was structurally tested at 29 psig and leak tested at its design pressure of 24 psig. A leak rate of only 1% of the volume per 24 hours was specified. Following satisfactory testing, a large section was removed from the steel dome to permit installation of major reactor components. The design of the HWCTR called for highly specialized equipment and components. For example, pumps of special design were built and tested at the Bingham Pump Company in Portland, Oregon. The shaft seals of these pumps would test their suitability for heavy water power reactor service. The reactor vessel was manufactured by the Pacific Coast Engineering Company in San Francisco, California. The overall height is about 30 feet, with a diameter at the core section of approximately 7 feet. It was fabricated from carbon steel plates and forgings 3.5 inches to 5 inches thick and weighs about 98 tons. All inside surfaces are clad with a 1/4 inch layer of Type 304 stainless steel. The vessel, manufactured in accordance with the Unfired Pressure Vessel Code of the American Society of Mechanical Engineers, is designed to withstand pressures of 1,500 pounds per square inch at a temperature of 600 degrees Fahrenheit. The vessel was shipped to the site by rail. It was installed in the reactor building through the large construction opening. The reactor biological shield has a minimum of 11 feet of concrete between the reactor and personnel areas of the building. The HWCTR is designed to test fuel and other components under simulated power reactor conditions. A neutron flux of up to 10 to the 14th is available in the test core. The necessary reactivity is provided by 24 enriched uranium driver fuel assemblies, positioned around the outer ring of the core. A driver fuel assembly consists of a single 2-inch diameter, 10-foot-long tube of 93% enriched uranium in a matrix of zirconium. Each tube contains about 1 kilogram of uranium, which constitutes 9.7 weight% of the alloy. Fabricated by the co-extrusion process, the fuel is clad with zircaloy 2 or zircaloy 4, with integrally extruded end plugs. Cruciform target leaves of stainless steel containing boron are positioned in the center of the fuel tube by a zircaloy support tube. This support and a ribbed outer housing tube define coolant flow on inner and outer surfaces of the fuel. The inner region of the core contains 12 test fuel positions in 2 staggered rings with 6 inner and 6 outer placings next to the driver assemblies. Inner positions will accept fuel elements of 3.5-inch diameter, and outer positions can accept up to 5-inch diameter test assemblies. Test fuel elements will be in the form of natural uranium metal or oxide tubes, or clusters of uranium oxide rods clad with zircaloy. Elements up to 10 feet in length can be accommodated. 12 control rods and 6 safety rods are located between the driver and test fuel regions of the reactor core. A cluster of 6 additional control rods is located in the center. 6 positions are provided within the test fuel core for in-pile instruments, such as axial flux monitors. The control rod drives and a lifting mechanism for the top head are attached to a movable platform, permitting clear entry to the reactor vessel. Loading and removal of fuel is accomplished by a shield transfer coffin with the head and control rod mechanism removed. A telescoping gripper mechanism designed to attach to special adapter fittings permits handling of fuel assemblies and other reactor components. The transfer coffin carries spent fuel assemblies from the reactor to an underwater storage basin, where they will remain until transfer to inspection facilities. In order to test fuel elements under a variety of physical conditions, the reactor vessel was designed with inlet and outlet ports to accommodate isolated coolant loops of the re-entrant type in the 6 outer test positions. 2 such loops, both fabricated of stainless steel, were installed during construction of the reactor. One can be cooled with liquid D2O at pressures up to 500 psi above the core pressure. Coolant enters the lower connection of the isolated coolant loop tube and flows downward through the annulus between the outer pressure tube and the inner housing tube. It is then forced upward past the fuel assembly and emerges at the upper connection. Coolant is then circulated through the shell side of a D2O H2O heat exchanger. The cooled D2O is then circulated through a surge tank and back through 2 centrifugal pumps to the loop tube. The loop is pressurized with helium at the surge tank. Rupture discs between this gas line and the reactor pressurizing gas system provide for pressure relief of excessive loop pressure. The other installed loop will permit tests at boiling reactor conditions. The loop tube for the boiling loop is almost identical to that of the pressurized water loop. The cooling conditions of this loop can be adjusted to provide operating conditions over a range of interest to boiling D2O reactors. Steam qualities from 10 to 30% can be obtained at the outlet of the loop tube. The resulting liquid-vapor mixture is condensed by liquid D2O in a steam quencher and is then circulated to the pressurizing surge tank. Pressure in this tank is provided by the reactor pressurizing gas system. The heated D2O is circulated back to the loop tube by two centrifugal pumps in series. Cooling is provided by a bypass of the pump discharge, which goes through a cooler similar to the liquid loop cooler. The cooled D2O is then used to quench the vapor from the outlet of the loop tube. Control is guided by the temperature differential across the steam quencher. The outlet steam quality is adjusted by the bypass rate through the cooler. Purification of the heavy water in the isolated coolant loops is accomplished in a common system. High-pressure makeup pumps feed separate head tanks for each loop and inject clean, heavy water into the systems. The two coolant loops of the main circulating system, including the steam generators, are fabricated of carbon steel. D2O, at about 420 degrees Fahrenheit, enters the reactor vessel through two inlet nozzles. It then circulates downward in a forced flow through each fuel tube, cooling the fuel. The reactor system is pressurized with helium gas. Heavy water leaves the reactor at the core section and is circulated by two 4,800 GPM high-pressure pumps. A continuous purge of moderator from the reactor through filters and deionizers maintains the heavy water purity. A pH of greater than 10, required to protect the carbon steel piping and components from corrosion, is provided by addition of lithium hydroxide to the system. Heat generated in the reactor core is dissipated through two large steam generators, each extracting approximately 30 megawatts of reactor heat at rated conditions. Light water is supplied to the steam generators from a system of wells in the area. Outlet steam is used to drive the feed water pumps for these units. The saturated light water steam, equivalent to about 60 megawatts, is vented to the atmosphere through a steam muffler. All reactor control operations are conducted from the adjoining control building, which houses the operating console, controls, and instruments for the operation of the reactor. In addition to control rods, control valves permit adjustment of the back pressure on the steam generators, and through the action of a strong negative temperature coefficient of reactivity, adjust the reactor power at almost constant moderator temperature. Inherent stability and ease of control characterize the design. The Health Physics Building, also located near the containment building, is equipped with the necessary protective articles which all operating personnel use before entering the containment building. A 10-foot diameter airlock on the ground level permits access during operation. The major goal of the HWCTR is the development of inexpensive natural uranium fuel elements which will withstand the long irradiation at high temperatures required for full-scale power reactors. Operation of the HWCTR will provide answers to many of the technical problems which must be resolved in development of the heavy water moderated natural uranium concept. The knowledge and experience gained from operation of the HWCTR can thus contribute immeasurably to the accomplishments of the power development efforts of the United States Atomic Energy Commission.